Hello friends, in this video lecture, we will see resource allocation graph that is part of deadlock. If we consider any graph G, then it has two elements. First one is the V, that is set of nodes, and E, that is set of edges. Same is the case with this resource allocation graph. This resource allocation graph is a directed graph that is used to represent deadlock in the system. It consists of set of vertices V and set of directed edges E, and it is shown there in the definition. G equals to V, that is vertices, and E is there for edges, set of vertices and the set of edges. Vertices V is categorized into two different types of nodes. First node, that is P, having n number of processes as shown here. This set consists of all active processes P and having n number of elements here. Then another set consists of all resources R having n number of resources. Then directed edges consist of two edges. First one is request edge, that is from process to resource R, and another edge is assignment edge, that is from resource to process. Whenever there is a request edge from process Pi to resource Rj, so it means directed edge from process Pi to instance of resource type Rj indicate that Pi has requested an instance of resource Rj and currently waiting for the resource. That is known as request edge or the requested edge. And after some time, that request edge is converted into waiting edge. Then second edge is assignment edge. It is directed edge from instance of resource type Rj to process Pi that indicate Rj has been assigned to process Pi, or process Pi has held resource type Rj. So this is known as assignment edge or the resource allocation edge, means resource Rj has been allocated to process Pi. Let's have example of resource allocation graph. So first of all, we will see resource allocation graph with no cycle. So here in this case, you can see there are four resources R1, R2, R3 and R4, and having three processes P1, P2 and P3. As I have told you earlier, whenever you want to represent resource, then you have to use rectangle, and whenever you have to use process, then you have to use circle. Means for processes we have used circle here, and for resources we have used rectangles. So whenever there is only one dot here in the rectangle under the resource type, then there is only one instance, and whenever there are two dots, it indicates two instances are there. Three dots there in the rectangle, that is three instances. Here, as per the definition of graph, we can say graph consists of process P1, P2, P3, R1, R2, R3 and R4 with different instances. These are vertices, and there is E, set of edges from process P1 to R1, R1 to P2, P2 to R3, R3 to P3, R2 to P2 and R2 to P1. So these are edges. So this number of vertices and number of edges forms the definition of graph, as we have seen in the previous slide. So in this resource allocation graph, resource type R1 has one instance, resource type R2 has two instances, R3 has one instance, and R4 has three instances. This graph describes that P1 has held an instance of resource type R2 and waiting for instance type R1. In this case, this edge is known as assignment edge and this one is known as request edge. Or we can say this condition is hold and wait type of condition. Another point is that P2 has held an instance of resource type R1, that is R1 towards P2, known as assignment edge, and instance of R2 from R2 to P2 is also known as assignment edge, that is shown with the help of H, means hold condition is there, and requesting for instance of R3. So this edge is known as request edge that turn into waiting edge. Then P3 has held instance of resource type R3, known as assignment edge, means we can say resource R3 has been assigned to process P3. In this case, we can say this graph does not form any cycle, means there is no deadlock. Then another example of resource allocation graph with cycles and deadlock. So this is the resource allocation graph. We are having three processes P1, P2 and P3 and resources R1, R2, R3 and R4 with different instances. Here we can say P1 has held an instance of resource R2 and waiting for an instance of resource R1, that is hold and wait condition. Then P2 has held an instance of resource R1, that is hold condition, and instance of resource R2. So P2 has held resource R1 and R2 and waiting for resource R3. So this is waiting edge. Then P3 has held an instance of R3 and waiting for instance of R2, that is known as waiting condition or the waiting edge. Here we can say P2 is waiting for R3, which is held by P3, and P3 is waiting for an instance of R2 where one instance has been held by process P1 and another instance has been held by process P2, and P1 is waiting for resource R1, which is held by process P2. So two cycles are formed here. First cycle is process P1, R1, P2, R3, P3, R2 and P1. This one is first cycle, and second cycle is P2, R3, P3, R2 and P2. So this is cycle 2 and this one is cycle 1. So in this case we can say the graph has cycles, then there are chances of entering the system into deadlock. The next one is example of resource allocation graph with a cycle but no deadlock. Here there is a resource allocation graph having 4 processes P1, P2, P3 and P4 and 2 resources R1 and R2 having 2 instances each. Here we can say P1 has held an instance of resource R2 and waiting for an instance of R1. So this condition is hold and this one is waiting condition. Then P2 has held an instance of R1, that is hold condition. P3 has held instance of R1, that is hold condition, and waiting for instance of R2, that is waiting condition. And P4 has held an instance of R2, that is hold condition. Here we can say P1 is waiting for R1, which is held by P2 and P3, that is one instance is held by P2 and another instance is held by P3. Then P3 is waiting for resource R2, where one instance is held by process P1 and another instance is held by process P4. So in this case, cycle is formed from P1 to R1 to P3 to R2 and P1. But there are no chances of deadlock because when P4 release instance of resource R2, then this instance can be allocated to P3 and this edge is converted into assignment edge to break the cycle. And another point is that P2 may release resource R1 and that instance of R1 can be assigned to process P1. Means this request edge, that is waiting edge, is converted into assignment edge. Means in this case we can see though there is a cycle but system cannot be there in deadlock condition. Here we can say if graph contains no cycle, then there is no deadlock. If graph contains cycle, if only one instance for each resource type is there, then system will be there in deadlock condition. If several instances per resource type is there, then there is possibility of occurring a deadlock. So these are 3 conclusions we can derive from last 3 resource allocation graphs we have seen. For more such videos, stay connected here with this channel. Thank you for watching.